You know, in medicine, we're always talking about boosting our immune system, right? Making our body's defenses stronger. But what if I told you that sometimes, to save a life, we have to do the exact opposite? What if we have to deliberately weaken them? Well, that's exactly what we're diving into today, the fascinating world of immunosuppressants.
I know, it sounds completely backwards, doesn't it? I mean, your immune system is your personal bodyguard, your army, fighting off every germ and virus that comes your way. So why in the world would we ever want to tell that army to just stand down? Well, it turns out there are a couple of absolutely critical reasons. First up, organ transplants. Imagine someone gets a new, life-saving kidney. Their immune system, as amazing as it is, just sees a foreign object and goes into full-on attack mode. We have to calm that response down. And then there are autoimmune diseases, things like lupus or rheumatoid arthritis. This is where the immune system gets its wires crossed and starts attacking the body's own healthy cells. In both of these cases, we desperately need a way to hit the brakes on that immune response.
Okay, so to really get how these drugs work, we need to peek behind the curtain at the immune system's command and control center. It all kicks off with one specific signal, a signal that activates a type of white blood cell called a T cell. You can think of this as the big red go button for a massive immune response.
All right, this diagram here, this is going to be our roadmap. Now, I know it looks a little intimidating, a little complex, but don't worry, we're going to walk through it step by step. This basically shows us the entire chain reaction happening inside that T cell from the moment it gets the signal all the way to the final order to attack.
So let's meet the main character in this whole drama, the T helper cell. This cell is basically the 5-star general of your immune army. Now, it doesn't get its own hands dirty in the fight, but its job is absolutely crucial. It identifies the enemy and orchestrates the entire attack plan.
So once our general, the T cell, gets its marching orders, a special messenger inside the cell called calcineurin just springs into action. Think of it as a runner, taking that go signal and carrying it deep into the cell's headquarters. This is what kicks off that critical chain reaction.
And what's at the end of that chain reaction? Well, it leads to the production of this incredibly powerful molecule called interleukin-2, or just IL-2 for short. The best way to think about IL-2 is like high-octane rocket fuel for the immune system. It's the green light that tells all the soldier cells to start multiplying like crazy and launch an all-out assault.
So, okay, if that's the process for launching an attack, it makes sense, right? If we want to suppress the immune system, we have to find a way to break that chain. We need to interrupt this pathway somewhere, and it turns out doctors have a whole toolkit with 4 different strategies to do just that.
Think about it. We can try to block the initial go signal right at the source, or we can stop the factory from producing the fuel, that's IL-2. What if the fuel's already made? Well, we can try to cut the fuel line so it can't get to the engine. And finally, if all else fails, we can just starve the army so it can't build any new troops. So let's break down how each of these strategies actually works.
All right, strategy number 1, block the go signal. We're going to go right for that key messenger we just talked about, calcineurin. The drugs that pull this off are called calcineurin inhibitors, and believe me, they are absolute workhorses in medicine, especially for preventing organ transplant rejection.
The 2 big players here are cyclosporin and tacrolimus, and the way they work is actually pretty clever. See, they don't block calcineurin directly. Instead, each one grabs a different helper protein inside the cell, and that new team, the drug plus the protein, is what goes and blocks calcineurin. So they're both accomplishing the exact same goal, just with a slightly different partner. It's kind of like using 2 totally different keys to jam the very same lock.
But of course, when you interfere with such a fundamental process in the body, there are gonna be consequences. These drugs are powerful, for sure, but they can be really tough on the body, especially the kidneys. It's a classic medical trade-off. And it's also interesting, right? You can see how even drugs in the same class can have their own unique side effects, like the gum overgrowth and extra hair growth you sometimes see specifically with cyclosporine.
Okay, on to strategy number 2, stop fuel production. So let's say we can't block the signal at calcineurin. What's the next best thing? Well, we can stop the cell from ever even making the fuel, IL-2, in the first place. And this is where a super common, you've probably heard of them, class of drugs comes in, glucocorticoids.
So how do they do it? These guys work right at the genetic level. They march right into the cell's nucleus, its command center, and they block a key protein called NF-kappa B. Now, by blocking that protein, they're essentially stopping the cell from reading its own DNA blueprints for IL-2 and a whole bunch of other molecules that basically just scream inflammation. The bottom line, no blueprint reading, no fuel production. Simple as that.
All right, that brings us to strategy number 3, cut the fuel line. So for this one, let's imagine the cell has already managed to produce the fuel. The IL-2 is made, it's out of the factory. What now? Well, our next best move is to make sure that fuel never ever reaches the engine. We've got to cut the fuel line.
And again, we've got a couple of really smart ways to do this. First, you've got a drug like basiliximab. It acts like a physical shield, literally covering up the docking port, that's the IL-2 receptor, on the outside of the cell. The IL-2 just comes along and bounces right off. Can't connect. Then you have another drug, sirolimus, which is even more sneaky. It actually lets the IL-2 dock, but it blocks the signal inside the cell, a pathway called MTR. So it's like the delivery was made, but the person who signed for it immediately shredded the package. The message is received, but it just goes absolutely nowhere.
But what happens if the signal gets through, the fuel is made, and it gets delivered? The immune cells are all fueled up, and they're ready to multiply. This brings us to our last-ditch effort, our final strategy, starve the army. We're going to take away their building materials so they can't make new soldiers.
I mean, think about it. To build an army of millions of new soldier cells, you need to copy a ton of DNA. And to copy DNA, you need raw materials, right? You need building blocks. In this case, they're called purines. So what these drugs, called antimetabolites, do is they shut down the factory that makes these purine building blocks. It's really straightforward. No building blocks, no new DNA. No new DNA, no new cells.
And hey, just like we saw before, we've got a couple of different tools for this job. You have mycophenolate and azathioprine. They both do the same thing. They stop purine production, but they do it by jamming up different machines along the factory's assembly line. Same result, different point of attack.
Now I need to pause here for a second because this is critically important. That second drug, azathioprine, has a really dangerous drug interaction. You see, it's broken down by an enzyme that gets blocked by a common gout medication called allopurinol. So if a patient takes both of those drugs at the same time, the azathioprine can't get broken down. Its levels in the body can shoot up to dangerously toxic, even fatal levels. This is a huge deal, and it really drives home why understanding these intricate pathways isn't just academic. It can be a matter of life and death.
Okay, so let's take a breath and zoom out a bit to see the big picture. We've just walked through 4 completely different strategies, and each one targets a unique link in that chain of command for activating the immune system.
So here it is, our whole journey, laid out in one place. We've got our 4 main strategies. Block the go signal with drugs like cyclosporine and tacrolimus, stop fuel production using glucocorticoids, cut the fuel line with basiliximab or sirolimus, or starve the army with mycophenolate or azathioprine. You can see it's not just about having one magic bullet, it's about having an entire toolkit to choose from.
And really, that's the whole point. By digging deep and understanding the incredibly detailed biology of this one little cell, the T cell, we've been able to develop this amazing suite of drugs. It allows doctors to act almost like molecular surgeons, precisely cutting in at different points to dial the immune response up or down, fine-tuning it for exactly what each patient needs. Having this power, this ability to literally edit our own immune response, it just opens up so many incredible possibilities. It really makes you wonder, right? As these tools get even more precise and even more sophisticated, what's next? What other huge challenges, from severe allergies all the way to cancer, could we finally conquer by becoming masters of our own immune system?